Okay, so today we're going to cover Chapter 6, Section 1. Today we're going to cover perpendicular and angle bisectors. So the first thing we're going to do is define what a perpendicular bisector is. And a perpendicular bisector is a segment, a ray, a line, or a plane that is going to be perpendicular to a segment at its midpoint. Before we can move on and cover the perpendicular bisector theorem, we need to define the word equidistant. And if you sort of look at it, it looks like it's trying to spell the word equal. So this is an equal distance, or in other words, the same distance. So this picture here, it's showing us that CP is the perpendicular bisector of segment AB. So here is CP. And I can tell that it's perpendicular because it has the right angle. And I can tell that it bisected segment AB because it split AB into two congruent pieces. It's got the congruency marks here. So point P is the midpoint of AB. So in this picture, CP is the perpendicular bisector of AB. And remember, a segment can be bisected. You can't bisect a line because we can't find the midpoint of a line, but a line can be a perpendicular bisector. So when you're looking for the perpendicular bisector, we're looking for the right angle mark and that it split the segment into two congruent pieces. We already talked about perpendicular lines in Chapter 3. So the perpendicular bisector theorem states that in a plane, if a point lies on the perpendicular bisector of a segment, then that point is equidistant. This is why we had to define that word from the endpoints of the segment. So in this particular picture, my perpendicular bisector is this line CP. So CP is the perpendicular bisector, and I can tell it's a perpendicular bisector because of the right angle, and then I can see that it split this segment AB into two congruent pieces. So because CP is the perpendicular bisector of the segment, then that tells me that segment AC here is going to be congruent to BC or CB, because they're both equidistant from the endpoints of the segment that was bisected. So AC or CA is congruent or equal to CB. You could also call this AC and BC. Either way. Let me add in another point that could be on the perpendicular bisector. So let's say I add in a point D here on my perpendicular bisector. So let's put this green, let me do it in black so it shows up. Here's point D, and then because D is on that perpendicular bisector, I know that point D will be equidistant from the endpoints of the segment. So here I could state that AD is congruent to BD because it's on the perpendicular bisector and it's going to be equidistant from the endpoints of the segment. Now we're going to see the converse of this. And remember, the converse is where we switch the if and the then statement. So the converse to the perpendicular bisector theorem, and this should be plane, not pane. In a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So here it says, if you're told that DA is equal to DB, and I can extend this line, then that tells me that point D lies on the perpendicular bisector of AB. And I can see from my picture the right angle and the congruency marks. So I can tell that this segment AB has been bisected by a perpendicular line. So segment or line CP is the perpendicular bisector of AB. Now, if it asks you to make some statements about this, let me go ahead and add in some equidistant segments from C. I could also draw, since C is on that perpendicular bisector, I could draw segments that go from C to B and C to A. And because C is on the perpendicular bisector, that tells me that AC here is going to be congruent to BC. Because C is on that perpendicular bisector. So some statements I could make about this picture. You could state that C lies on the perpendicular bisector of AB. You could make the exact same statement about point P and point D. So you could also say D lies on the perpendicular bisector of AB, or even point P. Because notice they're all equidistant from the endpoints of that segment. And then another statement, you could just say that line CP is the perpendicular bisector. So if it asks you to describe things that you see in the picture, all of these would be valid statements based off of that picture. So let's try some examples using the perpendicular bisector theorem and its converse. So here it's telling us that BD, line BD, is the perpendicular bisector of segment AC. And it wants us to find the length of AD. Well, since they told us that BD is the perpendicular bisector, that tells me that this will be a right angle. It is split segment AC into two congruent pieces. And I can also see that point D here is on that perpendicular bisector. So then point D will be equidistant from the endpoint. So D, DC, and DA are going to be congruent segments. So to find the length of AD, I first need to set them equal to each other, find the value of X. So I'm going to set AD equal to DC, or CD, it doesn't really matter. So 5X equals 3X plus 14. I'm going to subtract 3X. 2X equals 14. Divide by 2. And X equals 7. Now remember, it didn't ask me to find X. It wants me to find the length of AD. AD is equal to 5X. I'm now going to take my newly found value of X, plug it in. So 5 times 7, and the length of AD is 35. Divide by 3, and N equals 10. Now, it didn't ask me to find N. It asked me to find the length of YZ. And remember, YZ was equal to N plus 17. So I now need to substitute in 10 for the N, and YZ is equal to 27. And that's the answer to number 2. And now for number 3, I'll do this one in pink. So here it says to find WX. Well, WX is this little piece right here. Right here. And it's giving me the length of YW and WZ. So WZ is 20.5. So this piece here that we've changed each time is 20.5. So is YZ. And then they gave me the length of WY, it's 14.8. So for this one, I'm going to be using the perpendicular bisector converse, because since I've been told that these two segments have the same measure, then I know that WY has been bisected, and if I know the length of the whole thing is 14.8, all I have to do is 14.8 divided by 2, and I get 17.4. So the length of WX is 7.4. Again, each question was done in a different color. I just kept using the same picture over and over again. So number 1 was in purple, and I knew that it was the bisector, so I knew those two segments from point Z were equidistant from the end point. So that's how I knew that WZ was 13.75. And then number 2, I had to solve that equation, get the value of n, and then plug it back in. And then for number 3, I used the converse. Because the two segments, point Z was equidistant from the endpoints of the segment, I knew that that was bisected, and I just had to divide 14.8 by 2. Now we're going to talk about an angle bisector theorem. So the angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So in this particular picture, I can see that angle BAC here has been bisected because it's created two congruent smaller angles here. So because AD is the angle bisector, then I know that the two segments from a point in the interior of that angle will be equidistant to the sides of the angles. So this will tell me that BD is going to be equidistant from the sides of the angle to the angle bisector, as well as DC. So BD is going to be congruent to DC. And again, you could write the letters either way. So what we're looking for, whenever we're looking for a distance, we're looking for the right angle. So if you remember back when I talked about the banks of the river, and I wanted to swim across this river, and it was full of alligators, I would always want to look for the segment that was perpendicular. So that's what I'm looking for here, is the right angle on that segment to indicate that it is the perpendicular segment. Now we're going to see the converse of the angle bisector theorem, where we switch the if and the then. So if a point is in the interior of an angle and it's equidistant from the sides of the angle, then we know that it lies on the bisector of the angle. So here we can see that angle BAC, and then we have ray AD going through it. So because point D is in the interior of angle ABC, and we can see that it's equidistant to the sides, it's got the right angle and the congruency mark, then I can tell that AD bisected angle BAC, and that would create the two congruent angle pieces. So for example 3, on all 3 of these pictures, they want me to find the value of x. So in the first one, I'm going to be using my angle bisector theorem. I could tell that this angle here has been bisected by this ray because it created these two congruent angles. So then I can tell that these two segments here are going to be equidistant from the center. So x is going to equal 15. For B, I'm going to use my angle bisector converse. So because I've got the right angles and the two congruent segments that are equidistant from the sides of the angles, I know that these are two congruent angles because this angle was bisected by this ray. So I'm going to be setting 3x. So 4x minus 6 equal to the 3x plus 5. Subtract 3x. X minus 6 equals 5. Add the 6, and x equals 11. Now remember, on all of these, it didn't ask me to find any angle measures or segments. All it wanted me to do was find the value of x. And then for the last one, we're going back to the angle bisector theorem, and we can tell that this angle was bisected because of the two congruent pieces here. So that tells me that these two segments are equidistant from a point on that bisector to the sides of the angle. So I'm going to set 5x equal to 6x minus 5. Subtract the 6x. Negative 1x equals negative 5. Divide by negative 1, and x equals 5. Okay, so for the first thing we're going to do, now in the homework, they don't give you a picture of a graph. So you would have to graph it yourself. So step number 1 would be to graph the order pairs P and Q to create segment PQ. And it's already done for you, it's in blue. The second step is going to be to find the midpoint of PQ. And the midpoint formula is x1 plus x2 divided by 2, y1 plus y2 divided by 2. The order pairs I'm using are the order pair P and Q, which was given to me. And I could say this is x1, y1, x2, y2. It doesn't really matter. So I'm going to plug them in, and I get negative 2 plus 4 divide by 2, 3 plus 1 divide by 2. This gives me 2 over 2, 4 over 2, and then this gives me 1 comma 2. This is the midpoint of PQ. Because remember, the perpendicular bisector is going through the midpoint of the segment that it's bisecting. So now my next step is to find the slope of PQ. So step number 3, I need to find the slope of PQ. And then after I find that, I have to turn it into the negative reciprocal, which will be the slope for the perpendicular line. So the slope formula, y2 minus y1 over x2 minus x1, that's my slope. Again, same two order pairs. So these same order pairs right here. So I'm going to subtract my y's. 1 minus 3, 4 minus negative 2, negative 2 over 6 simplifies to negative 1/3. Now remember, this is the slope of PQ. I need the perpendicular slope, so I flip it upside down and make it opposite sign. So now my perpendicular slope is 3. So this is the perpendicular slope. Now, my next step is to write the equation. And what I'm going to use is the perpendicular slope, which is 3, and the midpoint. So 1 comma 2. I'm going to plug this into y equals mx plus b, find the b, and then plug everything back in. So I'm plugging it into y equals mx plus b. I'm plugging in 2 for the y, 3 for the m, 1 for the x, and I'm solving for the b. So 2 equals 3 plus b, subtract the 3, and the b of my perpendicular equation or my y-intercept is -1. So now I take the -1 and the perpendicular slope and plug it back into this. So my final answer, y equals 3x minus 1. These are the problems you need to show work for. 2, 6, 9, 11, and 12. Number 9 is the steps we just followed to answer example 4.